Mankind has taken a step forward towards space exploration by building satellites, but an even greater step is the invention of a CubeSat. Being tiny, light, cheap are some of its qualities. CubeSats are currently being used for data collection, picture taking, etc. But, ever thought about using it as a gateway between two satellites? You see, there are over 2,691 inactive or dead satellites that have become part of space debris. Some have been destroyed by collisions, while some by accidental health or power issues. So can we not use a CubeSat to help two satellites interact with each other, instead of having a satellite to first send the information to the ground station and then to the other countries? A CubeSat can help relay the information to other satellites, thus using less time and less expense.
We know that satellites require energy to stay in orbit and to continue their mission. But how is this energy gathered in the Hawking-Eye CubeSat? Just like any other CubeSat, Hawking-Eye gathers energy from the sun through the solar panels. Solar array usage is the best option for the satellite due to its massive energy, that is the sun. The 2U CubeSat with 8 solar panels can gather 9.6 watt of energy and is later on stored in the battery. During eclipse, the stored power from the battery is used. This CubeSat uses a lithium-ion battery. Power gathered from solar panels is also sent to subsystems like OBC, ADCS and COM. The attitude of the satellite is just its orientation. The attitude determination means to determine where the orientation of the satellite is, and the control of the attitude is to achieve and maintain a desired orbit using specific equipment. A CubeSat can use either spin stabilization or 3-axis stabilization. Spin stabilization is a way to stabilize satellite to spin in an axis perpendicular to the orbital plane. A 3-axis stabilization is the method of controlling movement of the satellite by having 3 reaction wheels on the Y, X and Z axis respectively. A A variety of sensors are used in ADCS. For example, magnetometer, which measures the Earth's direction in magnitude, sun sensor, which senses the direction to the sun to measure the position of the sun, Earth horizon sensor, which uses infrared or visible light spectrum to detect Earth's horizon, star tracker, the most accurate one, detects star and changes attitude accordingly, gyroscope, which determines the angular velocity of a satellite, GPS, which helps the satellite navigate. The satellite uses actuators to alter the attitude. The onboard computer OBC is half on the ground station and half on the satellite. Its job is to interact with the other subsystems, monitor the satellite's health and performance, and also controls it. It verifies and executes command from the ground station and processes sensor data from the ADCS and commands the actuators. OBC consists of hardware, software, and documentation. The hardware consists of a CPU, memory, bus, and the clock. The software includes the operating system, the software development tool, and the fault protection. Documentation includes requirement specification, design requirements, and the ICD, which is the interface control document. Tracking determines the position of the spacecraft and follows it using angle, range, and velocity information. It can determine the azimuth and the elevation angles, which can help determine the angle of the satellite. Telemetry is the gathering of the information on the health of the various subsystems of the satellite. The command is used to receive, verify, and execute remote control commands. The communication system of the satellite is included in the TT&C. The communication consists of transmission and reception. The transmission includes the coder, like the human brain, a modulator, a language, an up converter, whether to speak faster or slower, and a power amplifier, whether to speak louder or weaker. The reception includes an antenna, a low noise amplifier, a down converter which converts from digital to analog, a demodulator, and a decoder. The structure supports all the subsystems, attaches the satellite to the launch vehicle. The design has to be stiff and tough to satisfy the strength requirements. There are two types of structures, primary and secondary. Primary consists of the major loads and the secondary consists of wire bundles, a propellant, non-structural loads, and brackets for components. The structure is mostly made of aluminum alloy. There are a lot of temperature variations in space. The typical temperature in outer space is -170 degrees to 123 degrees. So the satellite has to regulate the temperature throughout all of its subsystems and structure. The thermal subsystem does this job. It consists of passive and active control. Passive control relies on conductive and radiative heat paths and no electrical or mechanical input whatsoever. Active control relies on pumps, thermostats, moving parts, and electrical power. The thermal subsystem further consists of heat pipes, electrical heaters, thermal clovers, heat sinks, solar reflectors, second surface mirrors, and thermal blankets.